Wes, you can explain a little bit of what we're seeing on the Analyze part?
Sure. So, so the Analyze module is essentially an implementation of a regression analysis, a standard regression analysis. The input that's required is actually pretty straightforward. In fact, there's enough information here to already run an analysis. So we have a dependent variable, in this case, the NIH Toolbox fluid component uncorrected. We have an independent variable, in this case, the NIH Toolbox pick vocab uncorrected. And so, and we'll go through the rest of the inputs in a second. But if I just click the submit button, it should take a few seconds to run. So here I'll just kind of walk you through the outputs. So we have several different sections of outputs from fitting the regression model. The first section is just the data display and summary. So it's just, in this case, it's just histograms of the dependent and independent variable. And so it gives you a sense for the distributions of both of the variables. And then if you go down, scroll down a little bit, you'll see some model outputs. The first model output is a scatter plot of the dependent variable versus the independent variable. And on top of the scatter plot, there's a regression line from the model fit along with a 95% confidence interval. The margins have the distributions of the margin of the dependent and independent variable residuals. And then if you click on, or if you hover over one of the points, it gives you information about the subject in terms of their NDAR ID and then about the different variables that go into the model. So for example, if you have an extreme outlier, over here, yeah. So here you can see that this person is from site 2, that they're male, they have a white, they have a postgraduate degree, and so on and so forth. So,
so this is actually a live plot. So you can, with the mouse, you can move the plot around, and you can also zoom in and out. So if you think that you before you do like a screenshot, if you want to adjust it, that's possible because it's a live display.
Mm-hmm. And so the next set of outputs are more information about the model. So the first is the model formula, and this is the R syntax that's used to run the model using the GAM4 function. This is the GAM4 module. And so we have a fixed effects component, which has the dependent variable, independent variable, and then hard-coded in are several fixed effects covariates, which I'll go back and talk about in a second. And then we have random effects in the model to count for the structure, the design of the study. So in this case, what we have is a random effect of site. So there's 20 sites in the data, and subjects are nested within sites. And then we also have within site, we have nesting within families. And so that's because there's a number of SID pairs, including twins, but also other SID pairs in the data. And we want to account for the correlation of the data caused by this structure, by the structure of the family in the site. So the random effects are defaulted into the model. And then if we scroll down a little bit more, the first table output is what we call table 1. And this is essentially a descriptive table of the data that went into the analysis. So for continuous variables, it gives you the mean and the standard deviation. And then for discrete variables, it gives you the number of subjects in each category and the percent of people in each category. And then the next output is the effect size table. And in this case, we're defining the effect size as the delta R square, or change in R square, going from the base model to the full model. In this case, the base model is the model with the covariate, the fixed effect covariates that are defaulted into the model. Those can be changed, but and I'll show you how in a second. But in this case, it was the 6 different demographic and SES categories that you saw in table 1, and then that's the base model, and then the full model is essentially the base model plus the independent variables that you put on top of that in the model. And so essentially the module is running both models, and then computes the R square for both, and then computes the change in R square. And then so the delta R square is the difference, the increase in R square going from the base model to the full model. The next output is an ANOVA table. So this gives a breakdown of the test for significance, the F-test of significance for each of the variables in the model. So you have the degrees of freedom, the F statistic, and the p-value. And then in more detail, we have the parameter table, and that goes through and that breaks out for every level of the factor, and for the continuous variables gives the regression coefficients is under the column estimate, the standard error of the regression coefficients, the t-value, and then the significance.
So there's one level missing here, usually.
Right. Yeah, that's a good point. So there's actually by default for categorical variables, there's a reference level, and so you'll see, for instance, for sex, the effect is sex M, or for male, which means that the reference category is female, and so this is essentially interpreted as the differential between the values for males and females in the study. So males have on average a negative 1.29 units less than females in the study, controlling for all the other variables in the analysis. And you can in fact change the reference level and if you go into expert mode, right?
Yeah.
Okay. So we'll briefly go over expert mode after this. And then the next output is the random effect table, and so this basically gives the standard deviation of the variance accounted for by the different random effects. So we have the family ID, so we have site, and then we have the residual standard deviation. So you can see, for example, that site has a standard deviation of about 0.5. Family has a standard deviation of about 5. So about 10 times as much of the variance the variation is accounted for by family than by site in this case.
So one mentioning the family in here actually just codes if participant belong to the same, if two participants belong to the same family. It does not include any information about twin status, about triplets, sibling, or twins in this case.
So yeah, and the twin status, the twin information is of course interesting for heritability analyses, but that'll be a separate module implemented not right now, but in future versions of DEAP. So the next output is model selection statistics, and here we have again the delta R square. We also have the Akiki information criterion and the Bayesian information criterion, and we have it here for the full model and for the base model. And the basic idea for both the AIC and the BIC is that a smaller value is better, so the model has better performance. And so in this case, you can see that both for the AIC and the BIC, there's essentially a decrease or going from the base model to the full model, or here an increase going from the full model to the base model. So the fact that these are significantly higher, or I should say they're quite a bit higher for the base model compared to the full model means that there's predictive utility in including the independent variable in this case. So, and then the final set of outputs are model diagnostics. And so the first one is a plot of the fitted values versus the residuals. And in a regression model, you're hoping that there's no pattern in this, so that if you do a scatter plot, it should be basically a random scatter around a line centered at 0, which is essentially what you see here. So this is the black line is a lowest plot, smoother. So, and then you can see maybe at the very end, there's a little bit of a departure from that, but it looks, relatively safe in terms of the assumptions of no relationship here. If you did see a relationship, for instance, if this was maybe a little bit more severe departure from 0 at the end, you might consider doing some transformation like a polynomial transformation or a smooth transformation. And again, we'll show you how to do that when we go back up to the top after this. The next plots are the predicted random effects, histograms of the predicted random effects for site and family. So again, you can see that they're on the same scale. So you can see that there's a much broader distribution of random effects for family than there is for site. And then the final plot is a QQ plot of the theoretical quantiles versus the sample quantiles for the residuals of the model. And for normal theory, for continuous models, the assumption is that the residuals are essentially normally distributed. And so from here, you can see if there's some departures from normality in the residuals. And again, if you do see departures, then you might consider doing transformations or there might be some outlying variables values that you might want to censor or consider treating differently. So we go back up to the top. So maybe we can go a little bit through detail the different aspects of the model.
So first of all, if that was too fast for some people, there is we're right now in compact mode, and we can switch to the tutorial mode, and then a lot of the information that was presented right now is available as text. So you can see text referencing the figures, and the figures each get figure captions that explain what is visible and how to interpret some of the values, how to do model selection, and what the different columns mean that are presented.
Mm-hmm. So, and then just for the rest of the demonstration, let's click back to compact mode. And so just for a little bit more detail for the model, so there's a number of other things we can incorporate or add or delete from the model. So for example, you'll see down here the fixed effects covariates. There's 6 kind of built-in fixed effects covariates, and they're highlighted in green. And these are variables that have been used to help design the ABCD study, in the sense that the sampling plan was put together to match to the U.S. population of 9 and 10-year-olds on these variables. And so we include these as default fixed effects covariates, as you saw in the model outputs, because the basic philosophy here is that if it's part of the design of the study, that we typically want to include those variables as part of the analysis. Having said that, there'll be situations where maybe you don't want to control for some of these variables, and so you allow for the ability to click off it. If you click off it, then the variables are no longer included in the analysis as fixed effects covariates, but the default is that you have them on. So you have to make a conscious decision to switch them off and not use them in your analysis. And then the second row of green buttons here is the random effects. And so again, we have a random effects of family and site. And the family we don't click off because it's generally a good idea to account for this. And as you saw from the outputs, that the family does seem to account for a pretty good chunk of variance in the model. And if you don't put it in, it's going to give you deceptive results, especially with respect to the standard errors of the regression coefficients. So we have the family built in and hard coded here, and you can't switch it off. Site you can switch off, and the rationale for that is if you're doing an analysis with brain imaging variables, that you might, instead of controlling for site, you might want to control for a scanner instance. In roughly half the sites, there's only 1 scanner, and then the other half it's 2 scanners. So scanner instance and site are largely confounded, and so you wouldn't want to put scanner instance and site in the same analysis. And so what we allow people to do then is to switch off the random effect of site, and then you'll have to add in scanner instance as a covariate in your analysis. And that's only relevant, of course, if you're working with the imaging data in particular. So for now, we'll leave this on.
Yeah. So how do you switch now to a particular variable of interest? In this case, we're looking at fluid composition and picture vocabulary tests. You can type into these fields. So you could say NIH toolbox, and then start typing, for example, flanker, and then use the uncorrected, and then press the submit button. That would change your model, and then the plots do change. What you can also do is each of these rows has a plus button at the end. So you can select that button, and that gives you a view similar to the Explore. So again, we can search for a specific variable and say picture vocabulary, and you can see some of the text here. If you select one of them, the variable name is copied in the lower right corner, and you can say add. And after adding it, the corresponding variable is now copied into the field. So again, we can say submit, and then the model will update again to the picture vocabulary test. If you left click on any one of them, they will turn green, and there is an additional window which shows the distribution of that variable. So maybe Wes.
Yeah, so maybe let's start with the dependent variable first, because there's a few more options for the independent variable. So if you click on the, as Hauke said, you left click on the variable, it opens up a little window that shows you a histogram of the distribution of the dependent variable. And it allows you to do a couple different things. For example, if the data were skewed, this actually looks quite normal, so I wouldn't do this in this case, but if the data were skewed, you might consider doing a log transformation, and then it'll update the histogram to show you what that distribution looks like. Clicking on it again removes the transformation. And then also, there's a censoring function. This is particularly relevant for some of the imaging data with the beta weights, but what it does is it removes the top and bottom 0.05% of the data from the analysis. And so if you do that, you can basically remove some of the extreme outlying values that you might encounter with some of the data. Here I'll just leave it untransformed. So if you select the independent variable of interest, again, if you left click on it, it opens up a box similar to the one with a dependent variable. But it has a couple of more different options that you can't use with the dependent variable because it doesn't make sense for dependent variables. So one of them is to do square transformation, and so this basically incorporates a main effect in a square term. So you can do a quadratic polynomial regression with the independent variable. You can also do a log transformation as above, and so that'll transform the independent variable using the log transformation. And then another one that doesn't appear in the dependent variable is a smooth transformation, and I'll actually run this one to show you what that looks like. So this gives you an empirically determined smooth effect of the independent variable. And that's why this is a generalized additive mixed model. The additive component means that it allows for empirically determined or data determined smooth transformations of the effect of the independent variable. So if I now click on submit, this one might take slightly longer because it's a little more computational, but like a second longer. So here, if we scroll down, we can see now the effect of the independent variable, the pick vocab, on fluid component is no longer linear; it's curvilinear, and this curvilinear relationship was determined, data determined by via using the smooth transform for the independent variable. So then if you scroll down, you'll see that the output's slightly different. So for example, the smooth effect now is given its own little row here, and you can look at the significance of the independent variable and the dependent variable with the smooth term in the parameter table. So what do you want to do next, Tauke?
Yeah, so you can see that the change in the field is actually visible. It adds an S, and if you select it again, you can disable this. Mm-hmm. You could also directly enter values into this field. So if you are interested in a smooth transform, it's easiest to do this with the smooth transform button, but you can do it separately as well. Mm-hmm. This becomes more of an interest if you add other independent variables, which in this case, you could say manually adding the picture vocab and using a polynomial model, for example. So again, you can type, and then you can select the field you're interested in.
You put in blanker uncorrected. And then if you want to, you can add in as many different independent variables as you want. So, and just to point out, the only difference between the independent variables here and the other independent variables and the independent variable here for which we're calling the independent variable for plotting is just the display of the plots in the bottom. So if you, it's impossible to try to make a display that'll work for every single possible combination of independent variables. So the way it works is that we have a main independent variable for plotting, and the plots will show the effects of that one, and not of the ones in the other. But they're treated the same essentially in the analysis. So so then you can do things here, like if you right click, left click, you can also do the same transformations here. You can also include now another one, which is an interaction. And so if I include interaction, then you can search there for another variable that you want to interact with. In this case, gender. And so now it adds in the two variables, gender and the NIH toolbox flanker, and includes their main effects plus the interaction term. And then you could stop there, or you could keep going and run the model like this. So here it's rank deficient because I think this guy. So we'll have to click that. Okay, so you'll see it doesn't change the model outputs in terms of the plots, but if you go down to the model outputs on the tables, you'll see that now there's interactions of the with the flanker with the gender included in the model, and you can keep going. You can add in more variables if you want to.
So we talked about the dependent, independent variables and the possibility to add more independent variables if they're required in the model. There are two more fields on the page that you can change and you can tailor your statistics for. One is the grouping variable. So if I remove the other independent variables and go back to our default model, I can open this up, and here I can also add the sex variable. So the difference now is that this again makes sex appear in the plotting function of the page. So you can add the sex variable as an independent variable, but if you add it as a grouping variable, then you will see the model output is now different.
Mm-hmm. And you can click on the different categories and see the regression lines for each, or you can look at both of them simultaneously. And then the individual points are then colored according to their levels on the categorical variable. And you can see that in the outputs as well that we now have the interaction of sex with the pictocat in the parameter tables. So that only works for categorical grouping variables, which we have predefined in this case. Are people capable of adding their own grouping variables, or
not right now?
Not right now. Okay, so maybe that's something we can do in the future.
For plotting,
yeah.
For the analysis, of course, because they can go in as independent variables. But
right. Yeah. Right. Yeah. For the plots, that's true. Right. That's a good point. Yeah. You can do any kind of interactions that you want to, as long as it's a variable in DEAP. But for the plotting functions, we have a predefined list for now. Mm-hmm. So I do want to just like basically show very quickly where the model is coming from. And so if you toggle on expert mode, it'll open up a window on the right, which gives you the R code that's being used to generate the models and the model outputs. And so this you can edit this directly. And so we're calling it expert mode because if you know R and there's certain changes you want to make, you can actually go into the code here and make those changes, and then run the model with those changes in it. And also, as we'll describe a little bit later, all of the code, all of the R code and all the outputs are downloadable. Maybe we can actually go over that right now and show people how to download the results. Or is there anything else you want to cover here?
Yeah, so there is, of course, the one set that we haven't talked about, the subsetting of sessions, but we will talk about this independently. Just to store a given model, that's basically the top part of the page. There is on the top left here a separate menu. If you open this up, you will see that there is the possibility to save the model under a given name. So we can go in here, call it something, save the model. This model is now listed under my username, and I can come back later and I can select this model, which will enter all the variables back into the interface. This is one way for every user to store models and to easily get back to them. We can also download a version of the model this way. So if you select the download button, what happens is that the model, which is the model specification, the raw data, those columns that are specified in the model, the analysis scripts, and all the plots that have been generated are packaged into a single file, a compressed file, and they will be downloaded to your current machine. We think that's one way to store an analysis, even outside the DEAP portal. It's one way that you can exchange this information with somebody else because the R code is inside. It is also a way to extend the GAM model that is provided on DEAP on your own. So if you want to use it as a starting point, it will have all the information in there to generate your own model.
Right. So the basic idea here is that DEAP, in particular the GAM4 module, is attempting to give people kind of a helping hand to perform analyses that we think are appropriate for the data, and then but we don't want to limit people to doing just the things that we have set up here. So one thing you can do is basically use the DEAP to come up with kind of a starting point with a basic regression, and then you can download the resulting R script and the data necessary to make edits to the code and make changes to it locally, and then run your model how you see fit in different ways. Having said that, we really highly recommend that everybody who performs analyses on on ABCD, and then uses that to publish a paper or make a presentation, makes that code publicly available to people to be able to replicate the results exactly. Because in theory, anybody who has access to ABCD has access to exactly the same data that you have, including the data here on DEAP. And so if you make that code publicly available, then that means that other people who outside your immediate research team can replicate your results exactly, which I think is important for reproducible science.
Yeah.
And you can actually then include that as, like, for instance, supplementary materials in a publication, or upload it to the GitHub repository that we'll take a look at a little bit later.
Yeah, and as more versions of ABCD are published, it also gives us the ability to run the same analysis on a larger data set or on a different subset of the participants to do like a built-in replication tests. Mm-hmm. So again, the menu that you saw here on the left, if I close it again, it's available on the top left, this hamburger menu, and you open it up, and that will allow you to store, save, and download models generated on this page.
So maybe we can go over the limit thing next. So selecting subset of sessions, or?
Yeah, so the one thing we haven't talked about right now is the subset of sessions. So you can make the analysis specific to a specific group, and that could be a demographic group, or it could be a group of participants defined by data quality. So if I open this menu, you can see here there's a public section. And after the public section, if you have defined your own subsets, you will also see your own subsets listed. The public section has like an easy example, all subjects. And if you select it and you run the analysis, everything stays the same. But you can select specific subsets, and these ones are examples. They're not necessarily making a lot of sense, but they're generated for you to be able to use them as a starting point to develop your own subsets. So females only, for example, would switch the analysis, remove all the participants that are male, and otherwise repeat the same model that we have here before.